Good evening, Chem Kids. This is a video on states of matter, liquids, and solids. You'd want to recall that we studied gases first because they were the simplest to study. In gases, the size of the particles didn't matter. The particles acted almost independently. But in liquids that we're studying now, size becomes a factor because the particles are closer together and the attractive forces take over. In gases also, the collisions were what's called elastic collisions, which means that there were no attractions between the particles. The particles would bounce off each other and not lose any energy due to friction. In liquids, there are attractions that hold the particles close together, much closer than in a gas. In solids, these particles are held even closer together, but they're so tightly packed in a three-dimensional structure that they can only vibrate in place. This slide talks about the importance of kinetic theory and its relationship to temperature. There is a direct relationship between kinetic theory, between the kinetic energy of a substance and the temperature. So the teaching is that any substance, whether it's a solid or a liquid or a gas, all substances at the same temperature have the same average kinetic energy. We call it average because there's always going to be some particles that are moving a little bit slower, some that are moving a little bit faster, but on the average, they have the same average speed. That's what the first line says, that we calculate the average kinetic energy in a substance of all the molecules rather than measuring it molecule by molecule, because that becomes almost impossible to do. At any temperature, all molecules of a substance have the same average kinetic energy. Again, it doesn't matter whether it's a solid, a liquid, or a gas. The kinetic energy increases as the temperature goes up, and it declines as the substance cools down, which means that the relationship is direct. There is a special temperature at which there is absolutely no kinetic energy whatsoever, and that is called absolute zero. Absolute zero is negative 273.15 degrees Celsius. We call that 0 Kelvin. What happens at that point is, theoretically, there is no kinetic energy, and if there's no kinetic energy, there is no motion of particles. The Kelvin temperature, not the Celsius, but the Kelvin temperature is directly proportional to the average kinetic energy of a substance. That means if the temperature doubles in Kelvin, so does the kinetic energy. Liquids and gases have something in common, and that is that they are both fluids. That means liquids and gases both flow. But liquids have attractions between particles that are even more than in a gas, not as much as in a solid, but enough so that it gives them something called a definite volume, right here. The physical property of every individual liquid is determined by the attractions that the molecules have for each other in a liquid and the motion that they have. We need to talk about this word vaporization. There's two kinds of vaporization. Vaporization simply means that a liquid is going into the gaseous state, and there's two kinds of vaporization. One kind is evaporation, and the other kind is boiling. As we're going to see, boiling has to do with the pressure, being at the right pressure of a system. Evaporation happens at the surface, boiling happens throughout the entire liquid. Let's talk about evaporation first. Evaporation is a phenomenon that happens at the surface of a liquid. There are molecules at the surface that have a little bit more kinetic energy than the others, and they are able to escape from the surface if the temperature is such outside. As you heat a substance, the kinetic energy of the molecules increase, and that means that those at the surface are able to take off more and more and more. Now, the interesting thing is this last little paragraph right here. When the fastest molecules leave the system, since they have the greatest kinetic energy, then what that means is that it lowers the average kinetic energy of the rest of the system. That was the example we were talking about in class about if I took all the highest grades in the class and removed them from the average, then the class average would collectively be lower. So if you take the particles with the highest kinetic energy and you take them out of the equation because they've left the surface of the liquid, then the average speed of the rest of them is going to be lower, which is why we say that evaporation is a cooling process. This next concept is very important. This is vapor pressure. Vapor pressure is the measure of the force exerted by a gas above a liquid in a closed container. That means that every liquid has little vapor molecules of itself above its surface, and these little molecules exert a force against the atmospheric pressure coming down. There's something called a dynamic equilibrium between evaporation and condensation in a closed container. If the container is closed, as many particles will be evaporating as are condensing. If you increase the temperature in the system, the vapor pressure will increase. More molecules will leave the liquid, they'll hit the container walls, and they'll recondense. We can measure vapor pressure in a special instrument called a manometer. Okay, we already did these kinds of questions on the last test, so we're not going to go through them. But just to let you know that, remember, the molecules here are from the atmosphere. The gas here is the one we're considering. This is mercury right here. And we can see that since this side is lower than this side, there's more pressure here, more pressure from the atmosphere. So this problem says that if the pressure were 760 mmHg, what would be the pressure of the gas? Since the vapor pressure is lower, we subtract 30 from 760 to get 730. Once again, these problems are not going to be on this test. We've already covered them in the chapter on gas laws. Vapor pressure of liquids. It's very important that you know how to read these graphs. There are three substances here: diethyl ether, ethanol, and water. On the y-axis, we have vapor pressure measured in torr. Remember, a torr is the same as an mmHg. And on the x-axis, we have temperature in Celsius. You have to know what a normal boiling point is. A normal boiling point is the temperature at which a substance boils at atmospheric pressure at STP, which is 1 atm, or in this case, 760 mmHg. What you do is you find the pressure, and then you go all the way, and you hit the line of the substance that you want to find the boiling point for, and then you read straight down, as straight as you can, and that is how we find the boiling point. For diethyl ether, that would be 34.5. For ethanol, that would be 78.5 if you go straight down, and for water, that is 100 if you go straight down. Liquids with a higher vapor pressure boil at a lower temperature. This is super important to know. Higher vapor pressure naturally, so the liquids that make easier vapor pressure on top of the surface, they will reach their boiling point much sooner than one where the liquid is not creating as much vapor molecules on top of the surface. Liquids with a high vapor pressure are called volatile. The boiling point of a substance is the point at which the particles throughout the liquid have enough energy to vaporize. At this point, the vapor pressure has equaled the outside pressure, the atmospheric pressure, and the liquid boils. Okay, we're now ready to talk about solids, and the kinds of solids that we're talking about are specifically ionic solids. There are also covalent solids, but we talked about covalent solids back in the chapter when we were doing molecular shapes like tetrahedral, trigonal planar, etc. For you to be ionic, you have to be a metal plus a nonmetal, or a metal plus a polyatomic ion. For you to be covalent, you have to be a nonmetal plus a nonmetal, and they have different properties. Ionic solids have a very orderly three-dimensional arrangement of atoms inside of a crystal system, of which there are 7. They are not easily compressed because the very definition of a solid is that the atoms are already as close together as they can possibly be. Solids are typically in such a closed packed type of system that they can only vibrate, and they do not flow like a liquid or a gas would flow. Remember, liquids and gases are fluids but not solids. The melting point of the substance is the temperature at which the solid changes into a liquid, and that is when the heat in the system gets those particles to vibrate so much that the crystal lattice collapses and the substance melts. The important thing to know is that the melting and freezing point of a substance are at the same temperature. Ionic substances, their shapes are one of 7 crystal systems, and they are orderly repeating three-dimensional structures. Ionic solids have very strong forces holding them together. The types of crystals are here. There's 7 of them. We do not need to know what they are. You just need to know that there are 7, and the way that they're patterned out is based on their length, width, and height. If the length is equal to the width is equal to the height, or is the height is different from the length and the width, if their internal angles are 90, or if they're 120, or if they're 90 and 120. So just know that the differences in the crystals have to do with their dimensions and with their internal angles. These are the types of shapes that ionic solids take, one of these 7 crystal systems. Allotropes. Allotropes are substances in nature that naturally exist in more than one crystalline form. The crystalline form does not have to be the same. They could be upright, slanted, they could be sheets, they could be spheres, they could be tubes. One excellent example of a substance that has allotropes naturally is carbon. So you need to know that carbon has allotropes, and the type of allotropes are, one of them is graphite, like in pencil lead. The other one is diamond. The other one is coal. The other one is something called Buckminster fullerene. And these are the balls. They're called buckyballs. There's something called non-crystalline solids. Not every solid is ionic, and therefore their shape isn't one of the 7 crystal systems. These are solids called amorphous solids, and they're very important in our world. They have no ordered internal structure, unlike ionic solids, which do. They include substances like rubber, plastic, and glass. And the way you tell the difference is how they melt and how they shatter. They melt not at a specific temperature like an ionic solid would, but they melt over a range of temperatures, and they don't shatter in more or less even angles and pieces. They shatter into irregular fragments rather than in specific angles like an ionic solid would. This is a phase change diagram, or a heating curve, and we get to see the 3 states of matter along with their transitional phases. So right here we have a close packed solid, and then we have a liquid, and then we have a gas. And in between, we have the transformation stages, which are solid to liquid and then liquid to gas. As we're going to see in another slide, the freezing point and the melting point are the same, and the vaporization point and the condensation points are the same. What's significant about this graph is also that the temperature only rises when the substance is in a pure state. So the temperature increases when the substance is purely solid, purely liquid, purely gas. But as you can see, and I'm going to do this in green, that as the substance is transforming from a solid to a liquid or a liquid to a gas, the temperature remains constant. That is very important, and all that energy is going somewhere. All that energy is going into transforming the substance from one phase to the other. All that energy is going into the phase change. Let's talk about phase changes. You need to know the names of all the different phase changes in a substance. Solid to liquid is melting. Liquid to solid, going the other way, is freezing. Liquid to gas is vaporization. Remember, we use this word when we're not sure whether it's boiling or evaporation. So this is a word that could mean either boiling or evaporation. This is a word that encompasses both because it means turning a liquid into a gas. And then finally, a gas back to a liquid is condensation. There's a special state called sublimation. Sublimation is when the solid goes directly into vapor. Solids have vapor pressure too. Some solids normally, in fact, the majority of them have vapor pressures that are very, very low. But occasionally you have substances such as dry ice or iodine where the vapor pressure is so high that the substance immediately goes into the gaseous state at room temperature. So sublimation is a special state where solids go directly to vapor due to their high vapor pressure. Again, it occurs in solids where vapor pressures exceed atmospheric pressure at room temperature. The opposite of sublimation is something called deposition. Phase diagrams. Let's talk about phase diagrams and phase change diagrams. Phase change diagrams have temperature on the side, and they have energy on the x-axis, and it is a stepwise progression. And if we were to label everything, we would say this is a solid, and this is a liquid, and this is a gas. And then at these junctures here, you would have a solid and a liquid and a gas. The temperature at which the solid turns into a liquid, that is the melting point. The temperature at which the liquid turns into a solid, that is the freezing point. And again, remember, it is the same point. So the melting point equals the freezing point. The same thing, and I'm going to do it in a different color, the same thing with the evaporation point and the condensation point. So the vaporization point and the condensation point are the same point. Remember, it usually takes more energy to turn a liquid into a gas than a solid into a liquid. And of course, going all the way from a solid to a gas, that is sublimation, and going all the way from a gas to a liquid, that is deposition. In phase diagrams, the graph is a little bit of a different graph because the y-axis is now pressure and the x-axis is temperature. And phase diagrams give us a whole lot more information than this heating curve or phase change diagram, because it brings pressure into the equation. Phase diagrams show at which temperatures and pressures each state of the substance can exist. They have special lines that separate the phases, and they have special points called the triple point and the critical point, which we will see in a minute. Here's a phase diagram for a substance. We can see that pressure is on the y-axis and temperature is on the x-axis. In fact, sometimes they're called PT diagrams or PT graphs. And again, right here, this is the line that separates freezing and melting. This is the line that separates sublimation and deposition. And this line here separates vaporization and condensation. The graphs almost all look like a Y, and where they meet in the middle, where all 3 points meet, that is the triple point, and that is the point where all 3 phases exist in equilibrium. It's usually at low pressures. and low temperatures. Then we have something called the critical point. The critical point, that's where the graph ends between a liquid and a gas. Usually, gases, the temperature can get so hot, but if you increase the pressure enough, you can always sort of talk the gas into coming back and becoming a liquid, except after the critical point. The critical point is the point at which the gas temperature is so high, so very hot, the particles are so far apart that no matter what pressure you apply to the substance, it will not become a liquid. So what you have to do is you have to imagine that there is a little box here. And at this point, if I erase this, at this point, the substance is in a new phase. It's called a supercritical fluid. And it is neither a liquid or a gas. It's in the special state where the particles are closer together than they would otherwise be in a gas, but further apart than they would otherwise be in a true liquid. Apparently, this phase has some interesting properties which chemists and engineers are just beginning to investigate. But anything past that point in the box becomes a supercritical fluid. This is the phase diagram for water. Again, we can see that pressure is on the y-axis and temperature is on the x-axis. We see that the triple point is at 4.58 torr and 0.0098 Celsius. We can tell where the triple point, where the critical point is rather, and we can see that at 1 atm, if you were to find the boiling point, you would go to atmospheric pressure, which is 1 atm, hit the vaporization condensation line because that's where a liquid turns into a gas, and read straight down, and you would get the boiling point, which is 100. If you wanted to know the melting or the freezing point for water, again, you would go to 1 atm, you would go all the way to the line that separates a solid from being a liquid, you would read straight down, and you would get 0 degrees Celsius, which is the freezing point of water.